We'll see. I'm not on the committee, so.
He's on that committee.
I know Dr. Skipper's the chair.
Yeah, I figured that.
All right. Well, I didn't receive, normally they send out an email and say, send your comments on both candidates, and normally they request it before the committee meets to discuss it. So I would have thought the committee is going to meet this week, but it could be early next week. So I think he left yesterday afternoon. So perhaps later today, Dr. Skipper will send out. I don't know what Skipper's class. Yeah, I mean, he might have exams that he's trying to grade.
Who else on the committee?
Yeah, so hopefully we find out something in the next week. I did ask him like when they would start, and it is looking like it would be August. And for good reason. He has a postdoc that the contract goes until then, and with COVID, he hasn't been able to get out to the museums, the Natural History Museum, or the herbariums, to get a lot of the samples. So he's relied on places like sending him, and he wants to try to get that finished. I think that it's an honorable thing to do. Also, if I was his advisor, I'd be like, look, I could get someone else to do it. Go get a job. Hold the job. Yeah. So we'll see. All right, so we did our exam. I haven't looked at them. I will. But I have the ecology exam to finish. Almost done. I'm working on the answer key. So we'll start grading those probably today. I'll start going through. What you'll note, I know you uploaded it to Blackboard, so there's a slot in the grade book. What I'm going to do is hide that slot so you don't see the grades until I get all of those graded. So sometimes I get 3, 4 graded at a time, and I have to take a break, go to class or whatever, and then I'll come back. So I don't want somebody's grade showing up, and then you tell your friend, hey, I saw my grades, how'd you do? And they're like, I get that email. I didn't get my grade. I don't see my grade. Well, I'll release it once they're all graded. Does it look like it'll get done by Friday? Probably not by Friday. So target's Monday. Get everything back. All right. And we'll see. Maybe it's on Friday. We'll see. But one of the questions was confidence intervals, 95% confidence intervals. So we did those, right? We could do it by hand, and then we did it in R Studio. Open. Right, so we had all these examples where we set up basically the mean of our vector plus our QT values, so our cutoff values, where the degrees of freedom is the length of that vector minus 1, as long as we don't have missing data, and then we multiply by the standard error. All right, so you get these confidence intervals that represent probability that the interval captures the true mean, because every time we take a sample, we can get a slightly different confidence interval. In some cases, we've got a confidence interval that maybe is too small, or maybe too large. You do this range and you say, man, this is a really large confidence interval. I want to improve my estimate of that true mean. So how do I do it? Well, it all comes down to the standard errors. That's really what it comes down to. Yes, the t-value, the critical value for the t-distribution is dependent on degrees of freedom, and that is affected by sample size. Well, sample size affects our standard error, and probably affects our standard error more than it affects that critical value of the t-distribution. So if we have really wide values and we want to improve our estimate, so shrink those confidence intervals, what we can do is decrease our standard deviation or increase our sample size. Now, how likely is it that we can actually decrease our standard deviation? probably unlikely that we can do that, right? Standard deviation is part of the sample. Maybe if we have error, like measurement error or instrumental error, maybe we can, if we can correct that, perhaps we can decrease our standard deviation. But other than that, we really have no control over the standard deviation of our measurements. Wing lengths of these roaches or tarsus lengths, you can't control that. But what we can do is control our sample size. If we're unhappy with our confidence intervals, go measure more. Go measure more items, collect more items, do more work. Increase that sample size so that our standard error shrinks. If our standard error shrinks, our confidence intervals shrink. All right. So how do we report the error? So normally what we do is report the error as our mean plus or minus the standard error. If we have a confidence interval, then we would put the confidence interval in parentheses as a range. And I showed you how to report the confidence intervals. But what we haven't addressed is rounding. How do we round these values? So we have this general rule. We take our standard error, we divide by 3, and then we note the first non-zero digit of that standard error. That digit is where we round our mean, and then our standard error goes to one more digit. All right, so let's say we calculate an average of 8.95312. All right, that's what R gives us. We haven't rounded it yet. And then when we do our standard error, we get 0.42189 repeating. Something like that. All right. So how do we round? We want to report it. We're going to do mean plus or minus the standard error, but we have to round. So how do we go about rounding it? Well, I gave you the rule. So we take our standard error, open this up, and we divide by 3. All right. So let's do that. I'm going to do it by hand instead of calculator. All right, so I take my 0.421897 repeating, going to divide by 3, right? Get to there. I don't even need to know anything else. Here is my first non-zero digit, and it's in the tenths place. So in the tenths place, that's what we're going to round our mean to. So this will be, so 8.95 we round. We want to round here. First non-zero digit, we look to the next digit, we're going to have to go up, so it'll be 9.0 plus or minus our standard error. But our standard error always goes to one more digit, so we round to that one more. All right? Not bad. So you can open up your R to do this. And what we will do is pull down that, I think the normality data. I think it would be a good one to use. So I already have this open, my markdown document open. I don't know where I read it in. Here it is, normality practice. I'm gonna go up here and got my standard error function. There it is. Gonna run my standard error, so I have it. Now in the normality data, remember I imported it, or you imported it, and then we use Q1 and Q2. Right. Q1 and Q2, and we use the na.omit, so we stripped out all of our missing data. So we're going to use Q1 and Q2. All right, so a rule. Divide SE by 3. First non-zero digit is where we round the mean. we round the SE to one more digit. All right. So example using Q1 from normality practice. CSP. All right. So we want to report the mean. Enter a task instead of a question. Report mean and SE as if reporting it in a paper. All right. So we have Q1. I'm going to take the mean of Q1 and I'm going to do standard error of Q1. So I'm going to calculate these values, and you can see I have multiple decimal points. Right. We want to report these values in a paper, in a scientific paper, or in a presentation, anything scientific. All right, so divide SE by 3. All right, so I'm going to do standard error of Q1 divided by 3. And I get 0.01131. So we go to our first non-zero digit. What is it? Hundredths, right? The first non-zero digit is the 0.01 place. So we round the mean to 0.01, and we round SE to 0.001. So we go to one more digit. So our write-up I don't even know what, it was just random data. We determined that the mean is, all right, 2.98 plus or minus 0.034. And whatever units it is. So, some of you might be wondering, how do we do plus or minus? Hopefully, some people have, right? Let me find it. Can't remember it completely, but we can do it. Let's see here. I think it is $/PM $. Yep, that's what it is. So if I knit the document, I'll do a note. /PM $. And I'm going to put this in quotes. Because I think if you put it in quotes, it doesn't execute. I could be wrong. Make a plus minus sign in the knitted document. Maybe I have to do single quotes. But you can do this $, for the backslash will add other things. Do you have to do it in a markdown document? No. If you just do plus and then the minus sign, I can see it. No problem. But if you're writing this up for, let's say, an honors project, could be useful. Could be useful. And if there's anything else, like Greek letters, email me or look it up, because that's kind of what I did. Our markdown, plus minus. And you talk about, how do you get it? How do you get it to work? Yeah, you'll find different hidden, different things to do. Pretty cool. So eventually you get fun. All right, so let's do question 2. So with Q2, from that normality practice, report the mean and standard error as if you were reporting it in a paper. All right, move this over. All right, hopefully you did this. So I've got the mean and the standard error. These are the values that we're going to report, but we have to figure out the rounding. The standard error of our vector divided by 3, I get this value. The first non-zero digit is that hundredths place, so round 2.01, and then the write-up, we recorded the mean as 3.99 plus or minus 0.095. So writing it like this way, plus minus, is sufficient for any of our work. Seems like a lot, right? But think about some of the general rules of rounding for our statistics. It's like when we talked about mean, my rule of thumb was always round or report the mean and round it to one more digit than your raw data. So if your raw data or whole numbers, your mean gets reported to the tenths place. If your measurement data goes to the tenths, report the mean to the hundredths place, right? All right, that seems to be a general rule. And why is that a general rule? It's because usually this stuff gets you to round to that point too. All right, so the proper way is to do the standard error divided by 3, figure out where you round it, then round your mean and standard error to that. And in most cases, it goes to that other general rule that I gave you, which was report your mean to one more digit than what we measured. So if I ask, and I will in exam 3, and on the final exam, report mean and standard deviations. If you're using it in a paper, this is what we're looking at. You got to use proper rounding. We have to use proper rounding. So I'm going to add a note. Again, just to kind of go back to our descriptive statistics. So in the descriptive statistics lectures, I told you to report the mean and round to one more digit than the raw data. This usually follows the SE divided by 3 rule presented here. So if you forget that standard error divided by 3, you forget this rule. If you fall back on what I told you about the descriptive statistics and how to report it, you're going to usually be okay. You're going to usually be okay. All right. So this is if we're reporting it in text, like writing it out in paragraph form. This is how you do it. If you do confidence intervals, put it in parentheses. Put it in parentheses and put the range. But oftentimes we don't really summarize our data in the text. Instead, we use the graphical methods. All right, so what graphical methods are there? Well, there are several different types, but all types that we prefer will report some measure, they'll report the central tendency. So they'll report either the mean or like the median. And then these graphs have to include some measure of dispersion. So either the standard deviation or the standard error. Very rarely, the confidence interval gets reported. Now, we do report confidence intervals if we do like bootstrap confidence intervals. And that's important if we know we're working with skewed data or non-normal data. Then bootstrap confidence intervals are usually better, and we can report them. All right, so what are our options? Well, one way is you can use a bar graph. I am against bar graphs because bar graphs are for frequency data. But if you have to make a quick figure in Excel, you can do a bar graph, and then you can add whiskers to it for the standard errors. All right. Now we can do like an XY scatter graph, or we can do line graphs and kind of add those error bars, but you have to be aware of the x-axis. What are the x-axis labels? All right, we don't want to have x-axis labels of like, one stem, two stem, three stem, four stem, and then we report like how many fruit are produced by plants with these different stems, right? And use that's a bad one. Yeah, we could. If we have 1, 2, 3, 4, 5, 6, and 7, we could use XY scatter, we could use the line graph for that. But if we have, let's say, colors of the flowers, red flowers, pink flowers, white flowers, or so forth, you might not want to use the line graph because you've connected your lines. So there's ways to do things. Are we going to make some graphs in Excel? Yeah, I'll show you how to make some graphs. Not the bar graphs. I'll show you how to kind of get some graphs together in Excel to present means and standard errors. But what we're going to use are Boxplots because Boxplots are built into R, and they're actually fairly easy to make. Oops. So rounding, these are extra practice. Do you have it? These? Do you have the answers to them? All right, so you can always, without looking at the answers, you could practice it, but I think our rounding's probably okay. So the graphical methods is a box plot. That's what we're going to use because it's built into R. And R has a function called plot, which will look at the underlying data that you give it and try to figure out what's the best plot to make. All right, so usually it's going to be this box plot for us. Box plots are good because they present everything that we need to know. It has a measure of central tendency. It has a measure of dispersion. Right? But there's a couple other things that it also does. One, it reveals potential skewness in our data, and it also reveals potential outliers in our data. So what are these box plots? Well, they're box and whiskers plots. That's what they're called. I just say box plot because the generic function in R is box plot. So the box plot is up here. The line in the middle, that represents our median. That is our measure of central tendency. Move this here. Shrink this up a little bit. There we go. All right, so this line here, these are our medians. The box is our interquartile range. So that is our measure of dispersion. All right, so our interquartile range, that's the 25th percentile, that's the 75th percentile, or the first quartile, third quartile. The skew is based on the position of our median inside of that interquartile range. If we are symmetric, so no skew, then this line will be in the middle. All right. When we look at these data, that looks, it looks like it may be slightly skewed, but it looks decent. It looks like we're close. This one, I'd say I'm leaning more towards some slight skew. And our skew would be skewed right because we tend to have some higher points up here. So median is our central tendency. That's the line. The box itself, the width of this box, or the height of that box in this graph, represents our interquartile range. That's our dispersion. Skew is the location of these lines inside of the box, and we should try to be close to the middle. And then we have the whiskers. So the whiskers will either mark the extreme value, so the largest and the smallest value, as it does here. So in A, that's our largest values up here, our smallest values down here. For B, we have our smallest value down here, but then we've got more points out here. So instead of this representing our largest value, this represents 1.5 times the interquartile range. Why 1.5 times? Because there is a generality that says that any point beyond that 1.5 interquartile range is likely an outlier. And some people would argue that you just drop those outliers from your data set. I'm not a big fan of that because it represents data. All right, unless you know you screwed up when you collected the data, then you could drop it. But if you don't, then no, you shouldn't. So, example, I'll use plants because he mentioned it. Arcane had mentioned it in the talk. So he measured like bulb size, right? So you can measure it by diameter of all these bulbs. Well, what happens? You pick up some bulbs, you're measuring them, you got your diameter, but then one bulb was right at the very bottom and it looks squished a little bit. That's one that might be an outlier, might be one of these upper ones, and I think we would be justified then in throwing that data point out because we think it was squashed, which if it's squashed, then it may alter our diameter. All right, so our box plots, medians, interquartile ranges, our skew based on the location, and then either the maximum value or 1.5 times the interquartile range. All right, so I do note, again, R doesn't use the 1.5 times the interquartile range unless there's a data point at or beyond that, or actually, if it's beyond that 1.5 interquartile range spot. So it'll be maximum. So it's entirely possible that our 1.5 times the interquartile range for this should be larger. Could be. R won't do that. So how do we do it? Well, I made this graph using this code. So you've got set the seed, you generate y1, that's normal. So y1 is our normal distribution, y2 is a chi-square, which is skewed. Right? And then I made just an x label, repeated it, and then I did a plot. So we can access it with boxplot y as a function of x, or we can just do plot. All right? Or we can just do plot. So we can do that. So let us do another example. Boxplots. All right, so we're going to generate some code. Oh, that was cool. Didn't know I could do that. Generate some data. All right, we're going to do 3. All right, we're going to generate three different data sets. So we're going to create our what should we do? We'll just do our letters. No, we don't want plot. We want we'll do site. All right. So what we're going to do is we're going to repeat site A. We'll do 200 times. We'll repeat B 200 times, and then we'll repeat, let's do C, let's do 300 times. All right, so we'll have 700 data points in here. All right, and then we have to generate our data. So Y1, we'll use normal distribution. So this will be our norm. Actually, we're going to round it. So round our norm. We want 200, and then we need a mean and standard deviation. So what mean do we want? 75. That sounds good. Mean of 75, standard deviation of, let's do 5. Get some variation in there. And let's round it to 1 decimal place. All right. We're going to round all of these. Just going to copy this round. 200, 300. So we will change this. So we'll keep it at 75, but this time let's increase it to 10, standard deviation of 10. So we've got two that are basically normal. And then for this last one, let's do yep. Which one? Oh, hold on. Yeah, like that. Let's get a non-normal distribution that is skewed. So let's do we'll do that. Now the negative binomial is skewed. What is mu? Okay. Let's see what they give as examples. Okay, we'll try that. I don't know if it'll work, but we'll try it. So we'll do Rn binom. We're doing 300. We're going to do mu is equal to I guess we'll do 20. Probably wrong, but and then we'll do size is I don't know, 50 maybe. Let's see if that works. Yep. All right, so we're going to set our seeds so that everyone gets the same answer. So what's the date today? 10/20/2021. That'll work. And then what we're going to do is make our vector. So this will be, we'll call it len for length. And this will be y1, y2, and y3. So I'm just going to run this chunk, and I've got site and length. And then I'm going to make a data frame on here. Data.frame of site and len. I'm going to call it dat for our data. So data's there. I've got 700 observations. I've got two variables. I've got a site variable that's A, B, and C. I've got a length variable that's our measurement variable. We've measured two, basically our tenths place. Made the data set. All right, and now let's make a box plot. All right. Generic function is plot. Y is a function of x, and then data. All right. So this will plot. This plots our measurement, our dependent variable, variable y, for against our independent variable x. All right. So R is going to look at this, and it's going to look at the x variable, and it's going to see that it is numeric. Not numeric, letters, strings, text. So it should look at that, and when we write our command, R will then say, okay, these are text, these must be factors, so let's make x categorical. And if x is going to be categorical, then R knows, okay, well, if I have categorical data, and then we're plotting a measurement data, I'm going to make a box plot. So I'm going to try plot of our length as a function of site, where the data that we use is dat. And I hope this works. No, it doesn't. So we need finite x limbs. And I think that goes back to here. So this was a change in a new version of R where it doesn't automatically make these as a factor. So back in our generating our data, I'm going to use the factor command. So factor, open and close, tells R that these data are qualitative data. So I'm going to rerun that. And then I'm going to try the plot function again. And now we get it.
Can you scroll up?
Yep. Oh, like that?
Yeah, just.
Yep. So this is why when we import the data, I said make sure your strings as factors is checked. Because that was an addition to R. I don't know why it isn't the default. Or it used to be. I don't know why it was taken out. It must be some sort of conflict with various data types. I don't know. But once they made that change, then the code, as how I had written it, no longer works. We have to use the factor command to tell R, take this vector of text data and make it qualitative data, or at least add the label qualitative data as a factor, so that when we issue the plot command, it looks at the data type, sees factor, and says, okay, I need to make a box plot. Do you have a question? Okay, something didn't. They are different rows. 500. Oh, rep B, yeah. 200. All right. So this is our box plot. So that's a generic function. If we want to force R to do our box plot, then we can use the box plot function. So box plot, y is a len as a function of site, data is dat, and it creates it. So I like just using plot. It works. It knows what I'm going to make. All right. And actually, the plot function takes the data, sees, oh, you want a box plot, and then it passes it actually right to that function. So either one will work. You can use plot or you can use box plot. It's going to work. And note, we'll look at these. So we know the first two, those are not skewed. So you can see our medians right in the middle of the box. All right, this one is going to be somewhat skewed. I don't know how strongly, but you see the outliers. So when we look at the whiskers, that's the minimum, that's the maximum. That's the minimum, that's not the maximum. Our maximum are actually these 2 points up here. So that point marks 1.5 times the interquartile range. That's how R makes it. There's also a function in a different package called bwplot. So the lattice package is a different type of package that allows us to make these box plots. I occasionally use this package for graphics because it has this neat feature here. This pipe symbol and then G. So that pipe symbol we saw when we were doing the Bayesian statistics we took a test on, right? Probability of actually having a condition if you test positive. So yeah, what this says is we're going to make a box plot of y against each x or each group in this variable. So if we did sites, let's say we also had seasons, all right, what we can do is use the lattice package to make a box plot of our length versus the site, but do a box plot for each of the seasons. We could do it manually, but lattice does it very quickly. Are we going to do that? No, we won't. I just present that here for completeness. Questions? All right, so box plots work. It's a great way to look at our data, especially in preparation for doing some sort of statistical test, like are the means equal? But sometimes the box plot isn't what you really want to report because it's a median, interquartile ranges, and what we're really interested in doing is comparing the means. If you're going to compare the means, then you probably need to have a figure of the means with some measure of dispersion. All right. standard errors work. But if you're ever working with non-normal data, then you have to have a different measure of the confidence interval. Because if we go back to these confidence intervals, this formula assumes that our data are normally distributed. Right? If they're normally distributed, we're symmetric around the mean. And these confidence intervals are symmetric around the mean. But if we're skewed, we're no longer symmetric. And thus these regular, what we would call parametric confidence intervals don't work. So what can we do? Well, we can generate what's called bootstrapped confidence intervals. All right? So bootstrapped confidence intervals. So what bootstrapping is a randomization method where we randomly sample our data. And we sample it with replacement. All right, so we're going to take our vector, our data set of, let's say, 100 values, and we're going to draw a new data set of 100 values using the values in our original one. So we're going to have a new data set. Some of those numbers will be in our new data set once. Some of them will be 2 or 3 times. Some of them might not appear. That's part of our sampling with replacement. And then with this sampling with replacement, we can take the mean of that and we can take the standard error of that to come up with bootstrapped confidence intervals. Now, the standard errors are still symmetric. And that's problematic if we have skewed data. So instead of reporting standard errors, then we report a confidence interval by looking at our collection of means that we've sampled and figuring out where's our 2.5 percentile in our data point and where's our 97th and a half percentile. That 0.025 and that 0.975 come back. We look at those values. That gives us a bootstrapped 95% confidence interval. So when do we do that? Anytime our data are non-normally distributed. All right. And it's good because, again, our confidence intervals reflect the underlying data of the underlying distribution of our data. So big advantage, no assumptions. We don't make that normality assumption. We don't even have to check normality. We just run a bootstrap standard error. Also, it's good for single value statistics, so proportions. If we did sex ratio, we talked about sex ratio in the ecology class. Sex ratio is a single number. It's 60% female. How do we calculate a confidence interval? Yeah, we can make assumptions and do a parametric confidence interval, but wouldn't it be better to take our own data and generate a new random sample to get this confidence interval that reflects the underlying distribution? Yeah, it is. So bootstrapping. So I think what we're going to do is probably stop here and introduce you to this entire idea of generating the bootstrapping sample. We're going to spend Friday going through it. I'm going to give you code. We're going to walk through what the code is doing, each point, because this randomization method is the same method that we'll use when we do randomized t-tests and randomized ANOVAs. All right. So let's go ahead and stop here, and we will pick this up on Friday. Any questions?